Okay, so section 2.5, implicit differentiation. So let's talk more about what this notation for the derivative means. Okay, so this means I'm going to derive the function that follows it. So derive f of x with respect to x. So if I look at the derivative of x squared plus 7, I'm going to apply my derivative rules to this function. I use my power rule to derive x squared, and I know that that's 2x, and the derivative of any constant is just 0. Okay, so implicit differentiation. What this would be is an explicit derivative. It means my function is completely in terms of x. I apply my rule, and I have my derivative as 2x. What if I asked you to derive with respect to x the function y squared plus 7? So now I have a function that can't be solved. It doesn't have any x's in it. I can still find a derivative, but I need a part of my chain rule in order to do it. So this is where my variable is. I derive y squared using the power rule, so I know that that's 2 times y. But now, because these variables do not agree, my chain rule part of it, I have to multiply by the derivative of the variable y with respect to x. Derivative of 7 is still 0, so my derivative would look like this. Alright, so this is your implicit step. So for implicit, you have to use a part of the chain rule. To derive all variables. That, and I'm going to put this in quotes, don't agree. Because when you use implicit, variables don't agree with each other. What do I mean by that? I want to derive with respect to x, but my variable in my expression is a y. These variables don't agree, so when I go to apply my derivative rule, I have to use the chain rule by multiplying by the derivative of that variable in the expression with respect to x. Alright, so let's look at a couple more uses of this. So find the derivative of the function x cubed times y. Okay, so when I look at this, I need my product rule because I'm multiplying two functions. I'm going to need my implicit step because I have the variable y here, and I'm deriving with respect to x. So the product rule, first times the derivative of the second. Now the derivative of y, alright, it's a function by itself, so the derivative would be 1. Bring the exponent down, subtract 1 from the original. Subtract 1. And now, because the variables disagree with each other, I need my implicit step here. Plus second function times the derivative of the first function. I'm deriving with respect to x, so I just apply my power rule and I don't need that extra added step. So cleaning it up, I would have x cubed dy dx plus 3x squared y. Now the derivative doesn't look nice per se, but that's the derivative of the function with respect to x. Alright, so now let's look at the derivative of an equation. Okay, so when I look at this to find the derivative of y squared would be 2y times dy dx. Okay, the variables disagree, so I need that implicit step. Plus 2 times dy dx plus 2x, and that equals 0. The derivative of 4 would be 0. Okay, so now look what we have here. We have an actual equation. So the goal is to solve for dy dx. Think about this notation. You've seen this. This represents the derivative of a function y with respect to x. So I'm going to first move this 2x term away from the dy dx. So think about solving an equation. The goal is to get dy dx alone. So I'm going to subtract 2x from both sides. Now on the left-hand side, I'm going to factor out a dy dx. Again, because that's what I'm solving for. And then my last goal to solve for dy dx, I'm going to divide both sides by that 2y plus 2. And the last simplification that I can make, I can divide each term by 2. So I'm going to write that as negative x divided by y plus 1. Okay, so find the derivative of x squared plus y cubed, x cubed plus y cubed equals 64. Okay, so apply the derivative rules. Derivative of x cubed is 3x squared. Derivative of y cubed, it's the same rule, but because the variables disagree, I need that implicit step. Equals 0. Solving for dy dx, I'm going to first subtract 3x squared from both sides. Now no factoring needs to be done here. Dy dx equals negative 3x squared divided by 3y squared. So my derivative, notice now my derivative is in terms of x and y instead of just being strictly in terms of x. Now where does that become important? If I asked you, write the equation of the line tangent to the function x plus y cubed equals x cubed plus y cubed at the point negative 1, 1. Okay, equation of a line. So we know it's going to be our point slope form. Where does the slope come from? It comes from, the value of the derivative at the point of tangency. So now when I look at my function has both x's and y's in it. So I will need an implicit step to find the derivative, which means my derivative is going to have both an x and a y in it. So when I go to find the slope, I need to plug in values for both variables. So let's work with the derivative. X plus y cubed equals x cubed plus y cubed. Okay, so on the left-hand side, I have my chain rule happening here. So how do we derive something to the third power? Bring that exponent down, subtract 1 from the original, and now what do? We multiply by the derivative of the inside. So the derivative of the inside, derivative of x is 1, plus the derivative of y is dy dx, and that equals 3x squared plus 3y squared times dy dx. Okay, now if I just asked you to find the derivative, you would have to solve this equation for dy dx equals some function. But I don't want the derivative. I want the value of the derivative at negative 1, 1. So what I'm going to do from here, I'm just going to substitute in all my x's get replaced with -1, all my y's get replaced with +1. dy dx is what I'm solving for, so that'll remain my unknown. Alright, so 3, -1 plus 1, quantity squared, 1 plus dy dx, and you'll see this will turn out real nice. 3 times -1 squared plus 3 times 1 squared times dy dx. -1 plus 1 gives me 0, so that whole term goes to 0. And I get 3 plus 3 times dy dx. So the value of my derivative, solving this equation for dy dx, subtract 3 and divide by 3. So I would get -3 divided by 3, so I get a slope of -1. So putting all this together, the equation of the tangent line y minus 1 equals -1 times x plus 1. Now we will continue to practice these in class. Okay, let's look at a derivative that uses, so find the derivative, cotangent of y equals x minus y. Alright, so applying our derivative rules, derivative of cotangent, negative cosecant squared of y. Because the variables disagree, I need to multiply by the derivative of y, equals 1 minus dy dx. Okay, so now I have my dy dx's on opposite sides of the equal sign. So I'm going to add the dy dx from the right-hand side, so that equals 1. I'm going to factor out dy dx now from the left-hand side. I get negative cosecant squared y plus 1 equals 1. dy dx equals 1 over 1 minus cosecant squared of y. Now let's look at this real quickly. If we do our Pythagorean identity, and it doesn't matter the variable, so sine squared plus cosine squared equals 1. If I'm trying to rewrite my functions in terms of cosecant, so cosecant's a reciprocal of the sine function. So I'm going to divide everything by sine squared. I get 1 plus cotan squared y equals cosecant squared y. If I solve this equation for cotan squared minus 1, now I'm going to divide everything by -1, and I would get 1 minus cosecant squared y. So now in here I can replace my denominator with negative cotan squared y. And what's the reciprocal of cotan? So my final answer would be negative tan squared of y for my derivative. We'll start with this problem tomorrow. Okay, so for homework, I would like you to try any 5 problems from page 146, numbers 1 through 15 odd, so you can check your answers on CalChat. Have a good day.